Hi, everybody. Dr. White back again, this time with section 1.4 on independent events. Let's go back to an example that we have already looked at. The one where we had 20 people in a room, and some were females, some were males, and we'd asked each person whether or not they owned a pink sweater. And remember, this was our data, okay, where I'm circling with my mouse. Now, we found that the probability, like if we picked a person at random from this group of 20, the probability of picking somebody who owns a pink sweater was 9 out of 20 because 9 people owned a pink sweater out of the 20. But we also found the conditional probability that a person owns a pink sweater if you know they're female was 8 out of 12. And that's from focusing, in on the 12 females, and 8 of them owned a pink sweater. And those two probabilities are simply not the same, okay? Now, let's look at another group of people, and let's say we ask them, like, what are you majoring in? And like, let's say this college, there's only 2 majors, biology and history. We also ask them about whether they own a pink sweater or not. And let's say there's 120 people in this group, okay? And 40 of them are bio majors, and 80 of them are history majors. And we find that like 19 out of the 40 biology people own a pink sweater, and 38 out of the history majors, of the 80 history majors, wear a pink sweater. So let's find the probability, if we pick a person at random, probability that they would own a pink sweater. Well, there's a total of 57 people own a pink sweater out of the 120, so 57 out of 120 is your chance. Now let's go for a conditional probability. Probability that you own a pink sweater if you know the person is a biology major. So then we focus in on the biology majors. There's 40 of them, and 19 of them own a pink sweater, so that probability should be 19 over 40. Now, if you multiply the top and the bottom of that fraction by 3, then you actually get 57 over 120. So it is the same probability. Knowing that a person was a biology major did not affect your estimate of the chances that they would own a pink sweater. And actually, the probability of their owning a pink sweater, if they're a history major, would actually turn out to be the same thing. The 38 over the 80 actually computes to the same thing that the 57 over the 120 would compute to. So it's like the major doesn't seem to make any difference, to whether or not you own a pink sweater, not for this group of people. So let's introduce some terminology. In the first example, the event of being female and the event of owning a pink sweater are said to be not independent. They are said to be dependent. In the second example, the event of being a history major and the event of owning a pink sweater are said to be independent. So the formal math definition comes on that question of whether the conditional probability is equal to the absolute one. 2 events, A and B, are said to be independent provided that the probability of A given B equals the probability of A. Simple as that. Now you can do a little bit of probability calculation, and they do some of this in the book, and you find out that if A and B are independent, then some other things happen. First of all, B and A are independent. It doesn't matter the order you say them. But also A and B complement are independent, and A complement and B are independent, and A complement and B complement are independent, okay? There's also a way to think about independence to help you with the multiplication rule. If your 2 events are independent, if A and B are independent, the probability they both happen is just the product of their probabilities. And the proof is pretty easy. The probability they both happen is the probability of the B times probability of the A given B. But if A and B are independent, then that probability of A given B is just the probability of A. And then you can just switch the factors around, and you get what you wanted. You've proved your result. Now, we can also talk about independence for more than 2 events at a time. For example, say you got 3 events, A, B, and C. They're said to be mutually independent if this happens, which is the same as saying that A and B are independent. If this happens, which is the same as saying A and C are independent, If this happens, which is the same as saying that B and C are independent, and this last thing happens as well, if all those four things happen, then the three events are said to be mutually independent. And that concept could be extended to, a larger number of events. Let's try some exercises here. Exercise number 5 says, hey, I'm just thinking about a couple of events, A and B. And I'm going to tell you that the probability of A is 0.8, and the probability of B is 0.5, and the probability of A or B occurring is 0.9. From that, can you tell whether or not A and B are independent events? Well, when I see those three quantities, I just think about that OR rule, from the early sections on probability laws. And I just fill in what I know. And so I get that 0.9 is 0.8 plus 0.5 minus the unknown probability of A intersect B. And then I can solve that equation for probability of A intersect B, and I got 0.4. Hope I'm right. Now, let's think about the probability of A times the probability of B. We were told the probabilities for A and B. They were 0.8 and 0.5 respectively. 0.8 times 0.5 is 0.4. Hey, those are equal. So the probability of A intersect B is equal to the probability of A times the probability of B. Well, we know that the probability of A intersect B is always probability of A times probability of B given A by the multiplication rule. And so if you set this together with this, set them equal, and you just divide out the probability of A, then you get the probability of B and given A is equal to the probability of B, which is the definition for A and B to be independent. So my conclusion is that these two events must be independent. Number 7. You got 3 people and they're playing football, and each of them is a field goal kicker, and each of them tries to kick a field goal, okay? And A1 is the event that the first kicker succeeds. A2 is the event that the second kicker succeeds, and A3 is the event that the third kicker succeeds. And all the kicks are said to be independent. So, like, I know the one person succeeded, it doesn't help to tell me any more about whether the other people will succeed. And they want to know in part A, what's the probability that exactly one player is successful? Sorry, there should not be 2 L's at the end of that. Well, let's see, exactly one player being successful. Well, that actually breaks up as the union of 3 events. You could first of all have player 1 be successful and then the other 2 not. A1 and not A2 and not A3. Or you could have not A1 and A2 and not A3. Or you could have not A1, not A2, but then A3 gets it. And those unions there are unions of disjoint events. So I can sum probabilities, and then because of the independence, I can use this new version of the multiplication rule where I just multiply out the probabilities for each of those events being intersected. And so I just read it off. The probability of A1 is 0.5. Probability of A2 is 0.7, so the probability of not A2 is 1 minus 0.7. And similarly for the probability of not A3. And then I get another factor here the same way and another factor here the same way. Cool. Part B asks for the probability that exactly 2 players are successful. I won't write out the solution here. You'll work the same as above, but here in each of these events, you're going to have only one of the letters being primed so that the other 2 can represent, people being successful. And so your computations will be very similar. Number 11 is another good one to look at in the exercises. Let A and B be 2 events. If A and B are known to be mutually exclusive, must it follow that A and B are independent? Or are there exceptions? Can they ever be independent? Or is this just never a possibility to be independent? What's going on here? So my answer, first of all, to the first little question is that they need not be independent. Here's an example where your two events are mutually exclusive but not independent. The random experiment that I'm going to trot out for you for an example is flip a fair coin once and just watch whether it comes heads or tails. And let's let A be the event that you get heads, and let's let B be the event that you get tails. So A and B are definitely mutually exclusive. Now, let me look at the probability of A given B. What's the probability of heads given that you get tails? Well, it's 0. Let's look at the probability of A on its own. Well, that's 0.5. Those two probabilities are not the same, so by definition of independence, A and B are not independent. Now, how about that second question? Can they ever be independent? I think they can, and here's my example. Again, my random experiment is going to be flipping a fair coin once. Let's let A be the event of getting 2 heads. So that's actually the empty event. The probability of it is 0. And let's let B be the event of getting 0 or 1 heads. That's actually the sample space, because you got to get either 0 or 1. The probability of B is 1. Now, A and B definitely are mutually exclusive. You can't get 0 or 1 heads and get 2 heads. But also, check out your comparison of the probability of A with the probability of A given B. Probability of A is 0, but the probability of A given B is 0 too. The chance of getting 2 heads, given that you get 0 or 1 heads, is definitely 0. So those are equal, and therefore, by the definition of independence, that the two events are independent. Exercise 17. Say you got 12 students, and each of them has a 12-sided fair die, a dodecahedron, I think they're called. And so it's got 12 sides, and it's a fair die, so it's equally likely to end up on any of the 12 sides. So each student has their own little die. And the students are numbered 1 to 12, and the faces of their dice are also numbered 1 through 12. So like I've got a dice where the faces are numbered 1 through 12, and you've got a dice where faces are numbered 1 through 12, and so on. And let's say all 12 students roll their dice independently of each other. Okay. What's the probability of at least one match? By a match, I mean that a student of a given number I rolls the die and it lands on face number I. Okay. That would be a match. What's the probability of at least one match? So this kind of feels like the birthday problem, or it feels like the hats problem. And I'm going to do it as 1 minus the probability of no matches. So it's 1 minus the probability of the and of 12 events. Student 1 doesn't get a 1, student 2 doesn't get a 2, all the way up to student 12 does not get a 12. Now, the probability that student 1 does not get a 1, well, there's 11 ways for it to come out not to be a 1. There's 12 ways for it to come out to be something. So 11 over 12 is that probability. And it's the same for each of these other students. It's 11 over 12. And because the dice are independently rolled, these events that you're anding up together here are independent of each other. So the multiplication principle just says multiply all those probabilities together. So there's 12, 11 twelfths multiplied together. So the answer is 1 minus 11 twelfths to the 12th power. Here's another cool problem. The last one we'll consider here. It's the duel problem. Abe and Bo engage in a duel. One of those old-fashioned duels, where it's a very honorable thing, where you get up really early one morning and you go to some forested area in Europe near the college where you have your leisure riotous existence, and you have your duel, and you've got your seconds behind you, but you're standing, 20 paces apart or something, kind of standing to the side with your pistol, okay, and pointing at the other person, and one person shoots and may or may not miss, and the next person shoots and may or may not miss, and you just keep on going back and forth like that until somebody gets hit, and whoever gets hit loses the duel, and the other person's the winner. So let's say that the two players differ in their accuracy. The probability that Abe hits when he shoots at somebody is 0.4. okay? The probability that Bo hits when he shoots at somebody is 0.6. So Bo's the better shooter. And Bo's very gallant and honorable. He says, so, okay, why don't, I'll let you go first, Abe. So Abe gets to go first. The weaker shooter gets to go first. What's the probability that Abe wins the duel? AW stands for the event Abe wins the duel. So here's one solution. Probability that Abe wins. Well, I'm going to think of Abe wins as the union of countably infinitely many events. Abe could win on that first shot that he takes. Or he could miss the first shot, and then Bo could miss his shot, and then Abe gets to shoot again, and he hits Bo. That's another way for him to win, you know? And that would be Abe winning on the third shot of the duel. Similarly, Abe could win on the fifth shot of the duel, the seventh shot of the duel, the ninth shot of the duel, and so on. Okay? So AWI, that just stands for Abe wins on shot I. Now, these events here in the OR, they're exclusive of each other. So I can sum their probabilities to get the probability of their union. And then I can think about how these events, well, the first one's really easy. It's just 0.4. The other ones, though, are ands of stuff, like AW3. It's the and of Abe misses on his first shot, and Bo misses on his first shot, and Abe hits on his next shot. And because all the shots are independent of each other, I am going to assume that. I'm going to assume that all the shots are independent. So it's like how you do on your previous shots has nothing to do with how you're going to do on this shot. Because of that, you get to multiply the probabilities. And the probability of miss times hit is 1 minus 0.4. And then, I'm sorry, this is a wrong. That is wrong. That should be 1 minus a 0.6, not a 0.6. Because, for Bo to miss, it should be 1 minus his chance of hitting, 1 minus 0.6. And then 0.4 there is the chance that Abe hits on that third shot. I don't think I got it wrong here with AW5. Let's give it a try. That's a chance that Abe misses first shot. Here's the chance that Bo misses his first shot. Here's the chance that Abe misses his second shot. And here's the chance that Bo misses his second shot. So you're up to the fifth shot, Abe's to shoot. And that's the chance that he hits that on that fifth shot. So I did get that one right. And so you just keep on going like that. And you'll notice what you've got here is every term is going to have a 0.4 in it because it'll end, with Abe hitting. And that's the 0.4 chance. And also, every term except the first one is going to have a 1 minus 0.4 and a 1 minus 0.6 is what it was supposed to be. And every time you move up by a term, there'll be an extra 1 minus 0.4 times a 1 minus 0.6 thrown in because of two missed shots, being taken to get you to that next stage. And so if you think about it, you could write that as an infinite sum with the summation notation that you learn in Calc 2. Sum as I goes from 0 to infinity of 0.4 times that little factor, 1 minus 0.4 times 1 minus 0.6, to the ith power. So that's what we call a geometric series. A series where each new term is the same ratio times the previous term. That common ratio this time is 1 minus 0.4 times 1 minus 0.6. And there's a formula for what they converge to. When the ratio term is less than 1 in absolute value, they converge to that little constant term, the 0.4, a constant factor, 0.4, over 1 minus the ratio term. So there is your answer, and you can compute it out to see what are Abe's chances of actually winning the whole duel. It's better than 40%, maybe even better than 50%. But why don't you get a calculator and see for yourself? While we're at it, let me show you another solution that sort of avoids summing the infinite series, and also kind of gives you more insight into how independence can shift your mode of thinking. Probability that Abe wins. Let me think of it as the union of two events. The probability that he wins on his first shot, union with the probability that he wins later on, shot 3 or later. Now those are disjoint, so it's the sum of those two probabilities. And the first one is easy, it's 0.4. Now let's think about what it means for Abe to win on the third or later shot. That is equivalent to Abe misses his first shot, then Bo misses, and then Abe wins on the third shot or later. And so I can think of that as the and of three events. Abe misses, Bo misses, and then Abe wins on the third shot or later. But wait a minute, think about the independence. Think about the independence here. Because all shots are independent. If Abe makes it to shot number 3, if he survives Bo's first shot, that's just like starting the whole duel out from the very beginning. And so the probability of Abe winning on that third shot or later is actually just the probability of Abe winning the duel. It's got to be the same number. So what you get is an equation that involves the unknown probability of Abe winning the duel. Solve it for probability of AW. Put probability of AW stuff on one side. Factor out probability of AW. Divide by. And there you go. You get the same stuff. Pretty cool, huh? So that's section 1.4 on independence. Hope you enjoyed this a whole lot. And see you again soon.